Jnanam Paramam Dhyayam. Knowledge is supreme.
Okay, so now we come back to our proof of the theorem, that is we want to prove that the ring is regular. So, proof of theorem. So, we have given that, okay, so we have two parts. So, we want to prove that so A is regular. Let us assume first A is regular. Then I want to prove that the global dimension of A is finite. This is what I want to prove. Alright. So, A is regular means the maximal ideal is generated by correct number of elements. Maximal ideal will be generated by A1 to AD, where D is the dimension of the ring. And we have seen earlier A is regular means it is a domain, integral domain, and therefore, this A1 to AD, these elements, this is called a regular system of parameters. This is called a regular system of parameters. And note that this has a property that if I go mod A1, A1 is a non-zero divisor in A. Also mod A1, A by A1, A2 is a non-zero divisor, A2 here is a non-zero divisor. In general, AI is a non-zero divisor in the residue class ring up to the earlier guy, that is AI minus 1. This is true for every I from 1 to D. Such a thing is also called a regular sequence. So, every time the dimension drops exactly by 1. That is the reason that this has this property. AI is a non-zero divisor mod this. So, in this situation, now I want to prove that the global dimension of A is finite. So, I want to prove that the homological dimension of the residue field is finite. This is what we want to prove. But to prove this, it is enough to prove that the homological dimension of the maximal ideal is finite. Because this M and A by M, they come in a short exact sequence where the middle term is A. Okay. So, what we just now proved in the lemma, you see here, if you have a non-zero module and A is a non-zero element, then the homological dimension of mod A is one more than the homological dimension of the module, and this is irrespective of whether M has a homological dimension finite or not. This equality always hold for you and for infinite. So, repeated application of this, it is enough to note that at 1 it happens, and that is so to prove this is finite, you prove this is finite and prove one more down is finite, and then its repeated application of this shows that homological dimension of M, A by M, is actually R. It's actually, what is the number? D. This is D. Because you prove that homological dimension of M by M is finite. That is where we have checked this corollary here. Yes, this one. If homological dimension of A by M is finite, so repeated application will tell you homological dimension of A by M is actually D, because so that already proves that the global dimension is actually this D. So in one stroke it proves the global dimension is finite and equal to also Krull dimension. So this is GL dim A. So this implication is put there. The next one, we want to prove the other converse. That means we want to prove that if the global dimension of A is finite, then M is generated by a regular sequence. M is generated by, if I prove that M is generated by A1 to AR with the property for each I, AI is a non-zero divisor in A mod the earlier elements, ideal generated by the earlier elements. If I prove this, M is generated by such a sequence of elements A1 to AR, so that AI is a non-zero divisor mod the earlier one. So then what will happen? That if I exhaust all the elements, the dimension of the ring will exactly drop by R. Okay, let us prove this first and then we will tie it up. Let us prove this. Okay. So these two. So I will prove that actually this R is dimension of A. Then also we are done now. This is what I will prove. This R is nothing but, no, this R, take R is mu by mu M, which is dimension of K is the residue field, M by M square. And I am going to prove that by induction on R, that M is generated by a sequence of R elements where each AI is a non-zero divisor mod the earlier ones. This is what I want to prove. So start with M. I know M equal to minimal number of generators of M is the dimension of this vector space. So any generating set, minimal generating set of M will have R elements. This is by Nakama lemma, and I want to choose such that the first one is a non-zero divisor, next one is a non-zero divisor mod the first one, and so on. This is what I want to choose, and that I want to do it by induction on R. So R equal to 0 means this vector space has a dimension 0 means M is M square. But that will mean M is 0. So then there is nothing to prove. Okay, so suppose now R is positive. And what do I want to choose? I want to start with one guy. So that means I want to produce a non-zero divisor in M, which is not in M square. Then it will be a part of a generating set for M. So look at M minus M square, and I am looking for an element A1 here, which is a non-zero divisor. This is what I am looking for. Okay, so if everybody is a zero divisor, if that is what I noted that no, if every element is a zero divisor, if every element in m minus m square is a zero divisor, then every module has a homological dimension 0. That is what we proved. But in particular, it will mean that this module, the residue field, this will have homological dimension 0, but that will mean that A by M is free, A module. That is not possible. The residue module can never be a free module, because here every element is annihilated by M. So, it can't have a basis. So, this is not possible. That means, there is an element in m minus m square which is a non-zero divisor. So, we choose that A1, we started. So, this we want to prove it by induction. No? So, if R is positive, then we can choose A1. So, there exists A1 in m minus m square, which is a non-zero divisor. This is not possible, not possible. Now, you go mod that. Now, look at the residue class ring A by A, and what is that we want to prove? That we want to prove that because now we have chosen a non-zero divisor which is not in m minus m square, therefore, this ring will have a finite global dimension. GL dim A by A is also finite, because we are assuming global dimension of A is finite, and A1 I should write A1 is an element in m minus m square which is a non-zero divisor. Under that assumption, we have checked that if I go mod A1, then also you get a finite global dimension for the residue class ring. Now, you do it by induction. Now, you apply to this ring A by A1, and the maximal ideal is m by m by A. This is the maximal ideal A1, and now you choose here a generating set A2 to AR, so that A2 is the non-zero divisor in this ring, and so on, the same property. So, choose A2 etc. AR in M such that A2 bar is a non-zero divisor in A by A1, and so on. So, AI bar is in this ring is a non-zero divisor in A bar mod A1 to AI minus 1, all these are bars. So, just lifting up, we get what we want. So, this implies there exists A1 to AR in M, a generating set such that AI is a non-zero divisor in A by A1 to AI minus 1. So, this means A is regular. So, therefore, A is regular. Okay. So, the most important thing why we proved this theorem. See, if you remember, we already knew that if A is regular, then the polynomial ring is regular in finitely many variables, or even the power series ring is also regular. But what we could not conclude is if A is regular and if P were a maximal ideal, P were any prime ideal, then A localized at P is also regular. This we could not conclude. And why we wanted that? Because we wanted to define a regular locus. So now do not assume the ring is regular. So A is arbitrary ring. And then we wanted to define regular locus to be all those prime ideals P in the spectrum such that AP is regular. So, for example, what will be the regular locus of a local ring? Regular locus of A, where A is regular local. This should be the whole spectrum. This was expected, right? So that means not only the maximal ideal is regular, but the localization is also regular. We have not proved this, but okay. So for this reason, we wanted to prove that if A is a regular local ring, then any localization of that is also regular local. So now that follows from the corollary. So let me write a corollary and then we will get back to this. Okay, A regular local and P any prime ideal, then A localized at P is also regular local. Okay, so this is much easier now, because if you want to test some ring is regular local, I have to test that the residue field of that ring has finite homological dimension. So we will show that the global dimension of the local ring A localized at P is smaller or equal to global dimension of A. If we show this by assumption, this is finite, this is by assumption, because A is regular, therefore the global dimension is finite, and if I show this, then this will also be finite. Okay, so that means what do you want to show? That means I want to show that, alright. So let us look at the module A by P. A by P is the module over A, and A is regular ring, A is regular local. So therefore A by P will have a finite projective resolution. We know that every module over a regular local ring is of finite homological dimension, and that is equivalent to saying that that module has a finite projective resolution. That means a projective resolution will contain only finitely many elements. So that is 0 here, then F0, Fn, and then it has become 0. All these Fi's are free modules. See, because over a local ring projective and free are same, I am writing them as F. So there exists a resolution as A modules for the A module A by P. And now let us localize this resolution, this long sequence where each terms are free and not this, and I want to localize this. If I localize it, then a localization is exact. So, this will remain exact. So, that means what? I am tensoring this sequence with A localized at P dash this. So, I will get 0 Fn tensor over A localized at P and so on, F0 tensor A localized at P over A, and then I will get this tensor with A localized at P is nothing but the residue field of AP. This is the residue field of A localized at P, and I have this, all these terms are free, these are free over, these are free AP modules. And therefore, this module as a AP module will have homological dimension in fact less equal to n. So, therefore, homological dimension of A localized at P of the residue field this is less equal to n, and this n was what? N was this homological dimension of this. So, therefore, global dimension, so therefore, global dimension of A localized at P equal to homological dimension of this is less equal to n, which is less equal to global dimension of A, because global dimension is by definition is a supremum. So, that proves this. So, now we have proved that, so arbitrary, so if you take any ring, arbitrary ring, arbitrary commutative ring, then we have this topological space spec, and I want to define a set reg A or equivalently Sing A. Okay, so this will be complement of that. And this is by definition all those prime ideals such that AP is regular. And now several questions, what kind of these sets are these? They are in a topological space. So, because they are complement of each other, whether it is open or closed and so thing like that. So, one would like to prove that the singular locus is a closed subset. In spec of A. But unfortunately, this is not true. Let us see one simple example. So, let us take an example A equal to field K x mod x square. So, it is a local ring. Is it regular? It is not regular because it is not even a domain. See, regular, if it were regular, it will be integral domain, but it is not even a regular. So, and what is the spectrum? It has only one prime ideal or maximal ideal. So, this is generated by x, small x, and the singular locus. This is not very good example, but it is extreme example. So, the singular locus is, this is the singular locus. So, it is not a proper subset in this case. So, one would like that actually this question one can improve, is it a closed set, and not only a closed set, it should be thin. thin in the sense it should have less number of elements, so that you have more elements outside that, or in other words this complement should be dense. So, you have a topological space and this whether it is closed and complement whether is it dense or not, that is the better question. So, that is first thing we need to assume, as we have seen in the examples earlier, that a regular ring cannot have more than 2 minimal primes, right. So, the irreducible components should not intersect, but in a fine, if you assume a good situation in the sense that if you assume that A is finite, A is reduced and finite type K algebra, where K is a field, then this is true, that the singular locus is closed and the regular locus is actually indeed a open dense subset. And this proof I have written in the third updated assignment. So, please read it there. So, one has abstractized this ring which has this property, singular locus is closed and regular locus is finite dense open. Those rings are called excellent rings, and there are nice theorems about excellent rings, that for example, ring of integers is excellent, polynomial ring over excellent is excellent, finite type algebras over excellent are excellent, and so on. One more thing just I want to mention here. You might have studied probably, if you have a field K, then GLN, this is subset of Kn square, and let us take for a simplicity K is the field of either real numbers or complex numbers, and then this on this you put a usual topology. Then this set is actually open. Open is not so bad to prove, open is much easier to prove, but is it dense also? Try to prove that this set is dense. This is very useful, because suppose you want to prove some formulas for matrices. For example, if you want to prove that if I have two matrices A and B, and I want to prove that the characteristic polynomial of the product equal to characteristic polynomial of the other way, PA, such assertion, suppose you want to prove, and you would have seen there one reduces to the case of one of them is invertible, and then proves it, because then one will be the conjugate of the other and so on. No? So, if you want to prove some formula for matrices or such thing, then one could assume that they are actually in GLN and then prove there by using. So, if you have a continuous formula which is true for GLN, then the same formula should be true for arbitrary MN, because the set is dense and the formula is continuous. So, you can always take the limits and prove it. So, that is very good for guessing things, for in general matrices what could be the formula, but it has to be continuous formula. But what does continuous means? It should involve only the plus, multiplication and so on, and those operations are continuous. That's it. So, we will stop.